Hi there, my name is Thaddeus Golden. I'm an FAE with Taoglas, and today I want to talk to you about RTK. So RTK is a differential GNSS technology that uses two receivers to basically get a much more accurate position than a standalone receiver could. One receiver is at a known point in space, so it's probably been surveyed. And when you know exactly where it is, you can basically correct out the deviations in your received GPS position at that point, and send that information to another receiver that is in the same vicinity, because the primary contribution to these uncertainties in your position are actually caused by the atmosphere. And so if two receivers are within a couple kilometers of each other, those atmospheric deviations are very similar. And so that's what allows this to work. But compared to a standalone receiver, where you might be getting 2, 3, or 4 meters of accuracy, with RTK, with very good antennas, you can get down to half a centimeter of accuracy, which is going to enable applications like autonomous vehicles or autonomous agriculture, commercial site survey, anything where you need that very high resolution. We've been doing some testing to determine which of our antennas are really best cut out for RTK. And so we've been playing with the Neo M8P. That is the new RTK receiver from u-blox. It's got RTK built in using the RTCM protocol, which is a standard RTK protocol. And basically what it allows you to do is it spits out a bit of information every now and again that you can send over some link, be it cellular or ISM or Wi-Fi, doesn't matter, just any way you want to connect these two receivers moving about. But, like I said, you need an appropriate antenna for this. So what makes an RTK antenna an RTK antenna? Well, our findings are that you need an antenna that can see a lot of satellites very strongly. I know, not a huge surprise there, but there are some certain signal characteristics that play into an antenna's ability to do so. So in order for RTK to work well, you need at least 6 satellites of one constellation, or 7 satellites of multiple constellations. It's just the way the calculations work. But generally speaking, in one constellation, you're only likely to see 5 or 6 at a time, and so having the view of multiple GNSS constellations really becomes critical for this to work robustly and work frequently. So you need a wide bandwidth to do multiple constellations, because they work at different frequencies. You also need a wide gain pattern that has a very strong gain toward the sky and down toward the horizon, in order to cast the net wide and be able to see as many of these satellite vehicles as possible. You can think of the low elevation gain as like your peripheral vision, where if you can't see well out of your peripherals, you're not going to see as many satellites as you might otherwise be able to see. You also need to have a fairly strong passive gain, because the way the RTK calculation works is that it looks at the phase of the carrier signal, and in order to know that phase well, in order to resolve it, you need to have a strong signal, because the stronger the signal is, the lower the relative phase noise is. So to that end, we have basically selected 2 antennas and pit them against each other. One is our 18 millimeter active patch. It's a small integrated patch module. It's got the LNA electronics on board, and sits on its own little ground plane. These are great for standalone applications, be it asset tracking or fleet management. They work really well for those lower precision kind of applications. But they do have limitations. So the gain upward is not quite as strong. You can see it on the pattern here that it tops at about 0 dBi gain. It also dimples a little bit around the horizon, so there's going to be pockets of lower gain in that angle space toward the horizon, which will limit the antenna's ability to see low horizon satellites. Also, because it's a bit lower gain due to that small ground plane, it limits the dynamic range of any single satellite link, and so you might not have the dynamic range you need to make that calculation successfully. On the other hand, we have AQHA.11. This is a physically larger antenna, but it is one of our highest grade antennas for L1 applications. It's a Quadfilar helical antenna, so that means you have very good gain both upward and outward. It's a peak gain of about 2.5 to 3 dBi straight up, and then a little bit closer to 0 dBi toward the horizon. But it's very even, and there's really no dimpling around that angle space toward the horizon. It's very flat gain pattern. It's also ground plane independent, so you don't need a large ground plane in order for it to work well. It just set it and forget it, pretty much. So how did these antennas do compared to one another? Well, we put them in the same environment, hooked them up to the same reference station for the RTK, and we looked at deviations in X and Y in position. We looked at deviations in signal strength over elevation, so from straight up down to the horizon, and we also looked at the percentage of successful RTK calculations, which is driven by that the dynamic range. And here's what we found. So the AQHA11 actually was able to get a hard fix 100% of the time. So it had the least uncertainty possible in an RTK kind of application. The smaller patch, it was able to resolve calculations about 36% of the time, but was not able to get a clear fix, and the remainder of the time it wasn't able to resolve any calculations at all. So looking at the X and Y deviation, we see up to 5 meters of deviation on the smaller patch, which is about analogous to what it would be in a standalone kind of application. The AQHA, on the other hand, was below 2 centimeters in deviation, so very, very accurate, perfectly suitable for autonomous vehicles or high resolution geofencing, anything where you need that very low deviation in position. And you can see here from the signal strength maps that there's a much more consistent signal noise ratio across that angle space for the AQHA11, which is driving its ability to do the things in the last 2 slides. The horizontal is the elevation, so that's going to be the consistency from straight up at the far right to down to the horizon at the far left. Also vertically, that's going to tell you how consistent the signal strength is, going around that upward axis. And so we see that it's fairly flat with fairly little deviation in both GPS and GLONASS, and has nice strong gain all the way down to about 30 degrees off the horizon. The patch, on the other hand, it's a little bit bandwidth limited, so it didn't do quite as well at GLONASS as it did at GPS. But around that angle space, around the axis straight up, there was quite a bit of deviation in the signal strength. You can see a very wide vertical spread, and so that tells you that some of the pockets around that pattern are hurting the signal noise ratio. But yeah, so that's kind of the summary. Now, the kind of pattern characteristics you need for RTK are also available in a patch antenna. It's just that typically you need a larger patch with a little bit more bandwidth and also a larger ground plane to get the best performance out of that patch possible. But for RTK, you definitely want the even gain pattern, wide beam width, and multi-constellation support for it to work best. And that's going to be, just a fundamentally superior positioning experience to the standalone kind of architecture. But you do need that extra well-known reference in order for it to work. If you have any questions about RTK, about which of our antennas would be suited for RTK, or any other questions about GNSS, please feel free to reach out. You can reach us at customer service at taoglas.com, or just go right to the website, taoglas.com, for more information. Thanks a lot and have a good day.